And of course, there's not a negative entry here. It's just using the glow discharge plasma itself to sample the liquid directly right into the plasma when we're doing atomic emission spectroscopy. Well, this gives you a little better idea of exactly how this is accomplished. This has been done by a number of groups now. But it's basically an electrolytic cell. Here we have the anode, which is usually a tungsten or titanium pin type of system. The discharge is sustained between the anode and a solution overflow. So we have a solution flow that's moving continuously down this glass pipette underneath the Weiss reservoir and then overflowing from the tip. We simply strike the discharge between the anode and the solution, which is the cathode. You get current flow, of course, through a ballast resistor, which will become important to make sure that the glow discharge doesn't devolve into an arc. That's important. The current flow would then move this way through the discharge, through the Weiss reservoir, and of course, since this is an electrolytic cell, we have a counter graphite electrode. We actually separate it with a polyethylene divider to make sure that the hydrogen that's involved there doesn't perturb the plasma itself. It's an interesting discharge. This is a picture here shown on the left of what it looks like when it's running this typical tap water from our laboratory. You can see actually the sodium emission here that's sitting right on the cathode surface. If you look at it a little more closely, you can see that it has a lot of the spatial structure that is typical of even reduced pressure flow discharges. So the anode here is at the top. Most of the discharge is actually the positive column, so there's a relatively low electric field there. And then we have the cathode surface, so you can see the negative glow here, and the cathode that is the solution. And in most cases, we see atomic emission right from that surface cathode environment, since that's where most of the most energetic type of excitation mechanisms occur. Here's a little better photographic evidence that'll give you a better idea. I hope that came out a little better. But you can see here that this happens to be a titanium anode. You can see the surface of this quartz capillary that we use as the counter electrode. And hopefully you can see the atomic emission from here, thallium, yttrium, and indium. Again, just visually you can see the emission from the atom line that is right on the cathode surface. So it really is a glow discharge in the ambient atmosphere that's capable of producing atomic emission spectroscopy. And I thought I would do this, show you a couple movies to give you a little better picture of exactly how this thing operates. So this is me in my movie making mode that will show you the thing running. This is a titanium anode. I hope we can turn down the lights just a little bit. And the solution, which is a cathode here, which is containing nitric acid. You see the anode move down and touch the solution cathode surface. You see it immediately operates or strikes. And the interesting thing is the surface here is almost a negative meniscus. If we turn the lights off, you can see exactly the solution cathode glow discharge. And then I'll shoot a Heine laser through it. You can see how violent that environment is as the droplets move off. I don't know if you can see that very well in the back. But you'd have to take my word that there's a bunch of droplets that are moving off the solution surface, which is not surprising when you think that this glow discharge has a measured gas temperature of about 3,000 degrees. And it's sitting right on top of a condensed phase liquid. So that's kind of one of the avenues that we're interested in. We're interested in actually applying this thing in field type areas, but we're also interested in the atomic or the plasma spectrochemistry that would allow a plasma to sit right on top of a condensed phase liquid. So in the past, what we've been doing is a lot of laser strobe experiments. So to orient you, the anode here is at the top. Without the lights off, it's going to be difficult for you to see. But the incoming laser strobe here is moving out of the board. And the surface of the solution cathode is right here. So the solution is moving up and then overflowing from the top. And again, you might have to take my word for it, but there in fact is a bunch of what appear to be small plumes along the surface of this system. Maybe this one will turn up a little better. Can you see that in the front? These are actually small Taylor cones that are being formed on the liquid solution surface. So the electric field is high enough that you're getting the electrospray ion type of formation right into the negative glow where desalvation and excitation occurs. I'll give you one more movie that will give you an idea of how high that electric field can be. This is now a high-speed movie that we took in ambient conditions, ambient light conditions. Again, the anode here is at the top, solution cathode is at the bottom. As it moves down, you can see first the solution free energy changes significantly because of the high field there. That means that we go from a positive meniscus, as we typically see in a glass water interface, right into a negative meniscus. The other interesting thing is the formation how quickly this thing stabilizes. Now, this has been a source of a lot of interesting work in our laboratory, trying to figure out exactly what's going on. The most recent thing that we've done is Schlieren imaging. So Schlieren imaging takes advantage of differences in the refractive index within an image in order to get visualization of an object. That is to say, typically the gases that we see, ambient wavelengths, you can't tell if it's water or if it's liquid or argon. However, if you look at their refractive indexes, because they're different, you're able to actually visualize where they are within an image. This will become clear here as I show you the movie. So here we have the anode, again, and the solution cathode down here. And what you see is that you don't see the discharge itself. What you're seeing are the differences in the refractive index. And those differences are due to the difference in the water vapor composition, as well as the difference in the temperature of the ambient gas. So these light spots would be areas of high or higher refractive index, and the contrast would change with increasing refractive index. So the interesting thing is when you start doing high-speed movies with this type of information. So what you're going to see here is, again, one of these lighting effects. We like to look at the lighting stage of the discharge, since that gives us an idea of how quickly it stabilizes. The first thing you see is the anode move down and see the surface, and then you see what looks like a rocket taking off. It's interesting because the hot gases should actually be moving up. So instead of gases that are actually moving up from the solution cathode of the discharge, we're seeing them propelled by the electric field to the surface of the liquid. This is called ionophoretic flow. And the speed here is on the order of about 100 meters or 1,000 meters per second. So these things are moving very quickly to the solution surface. And this is fundamental plasma physics that's kind of interesting to us, trying to figure out exactly what's going on. Now you might be asking, why do we care about this thing at all? And so I'll give you some actual applications where we use this in the field. This is a typical setup, as I said before. This is a cell. We're just doing simple atomic emission spectroscopy, a high voltage power supply that's pushing 850 to 950 volts. You have a balanced resistor here on the order of the kilo-ohm, which means it's about 75 watts of power. And if we take that and we do detection limits and compare them to what we can achieve with our ICP OES type system, you see that it's competitive in many regards. Here are the elements, vertically, solution cathode flow discharge that I've talked about, the scale that I've been using before, and something called a mini solution cathode flow discharge. So simply we've taken the scale and decreased it by about a factor of 2. And we compare them to the detection limits that you can get with a typical OES type of instrument. You'll see in many cases they compare quite well with something that has a power consumption of about 100 watts. And in some cases it can do even better. The lithium and sodium here at the bottom, you get fantastic detection limits. And that's because it's a really good anode reservoir. It's not hot enough to cause a lot of ionic emission lines, but you see a really good anode density, which makes it an efficient source for both atomic emission spectroscopy and probably AAS and AAS as well. And I think we'll hear something about that at the Asian Pacific Winter Conference. The limited dynamic range is between 4 and 5 orders of magnitude. In terms of the matrix effects, we see minimal matrix effects below, say, 100 parts per million of concomitant element. And we typically see the EIE type of matrix effects as well. And if we look at the detection limits that we've determined for a number of elements across the periodic table, the first thing, of course, is that we don't look at the anode materials, since there's obviously would be a problem. For those that give really good detection limits, they're either the alkali metals or the alkali earths, or things that are good emitters, silver or indium, for example. And that's below, let's say, a part per billion, pretty reproducibly. The bulk of the elements fall between, say, a part per billion and 1 part per million in terms of detection limits. And then we have some, the typical example of mercury. Mercury is an interesting element in that it forms a lot of oxide in the solution. So instead of emission, people have been using this as a way to nebulize material into, say, an inductively coupled plasma OES or AES system. Then we have some bad actors. These typically happen to be the ones that have high oxide bond length, or bond strength, sorry. And this, in retrospect, makes a lot of sense because what we have here is really a liquid vapor plasma. And And when there's a lot of water or a lot of OH around, we tend to form the oxide, which is hard to break apart, therefore we don't see a lot of atomic emission. And in fact, a lot of elements we actually determine as the oxide, yttrium and lanthanum being good examples. So you see this is kind of an interesting glow discharge plasma. The chemistry is different. We have to think about how we apply the spectroscopy. But in terms of doing direct liquid analysis, this might be a nice low-cost, continuous type of field portable instrument. Now, the last kind of couple minutes that I have, I want to talk about gas analysis and actually move into the realm of molecular mass spectrometry, because we think that glow discharges have a really useful application in what's known as ambient mass spectrometry, which those of you who follow the mass spectrometry literature know is this is the new hot deal, to be able to take an item and place it directly in front of the mass spectrometer and tell something about the molecules that are on the surface. So the advantage is being that you can sample molecules directly from their native chemical environment and ionize them within the ambient atmosphere. There's no sample preparation or things like that. We can think about using a glow discharge in order to accomplish that. Glow discharge is one of many different ambient mass spec sources that have been reported in the literature. But the one that we've been looking at in our laboratory is a helium-supported atmospheric pressure glow discharge that we call a FAPA, flowing atmospheric pressure afterglow. It looks something like this. And this is atmospheric pressure. We have a pin anode and a plate cathode in which we drilled a small hole in the order of about 1 millimeter or so. It's a helium-supported discharge flowing at about 800 milliliters per minute. And that helium gas moves through the discharge, creates reactant ions, excited neutrals, as well as electrons, which then pass into the ambient atmosphere. We place our sample here, right in front of a mass spectrometer, and we can analyze molecular ions that are created in much the same way that, say, APCI sources operate. The reactive species that we can create are really interesting. For the most part, what you see if you look at the background of what we call reagent molecules, these are protonated water clusters that are formed in APCI. They're known to be one of the major sources of hydrogen proton transfer ionization in APCI type of situations. But not only can you do that, but you can think about creating other molecules. Oops. Well, we just have to take my word for it that you can form charge exchange reactions, such as nitrogen oxide. I'll give you 2 examples. One is the direct analysis of chemical warfare simulants, here by gas chromatography separation before we inject them into the afterglow of our FAPA source here. Here are 4 of them along the time axis according to chromatography. You'll see that each is about 20 nanograms on column. So the time response is really fast. There are a lot of reagent ions that are created, and it's a very simple way of doing it. But of course, what you really want to do is this direct desorption of species right from a solid and ionizing them, so you can think about taking an orange and placing it in front of your mass spectrometer, or maybe doing direct urine analysis and looking for drug metabolites, and that's what we've done here. This is a direct dip probe that was placed into a urine sample, which we happen to know there were a lot of standard drugs of abuse. We simply took it, placed it in front of an MS that we have in our lab, and the first peak you see, of course, is creatine, which has a really good gas phase basicity, and therefore it's the major peak in the spectrum. Of course, the student that did it the first time thought, oh, well, that's not going to be a very successful application. But if you actually look down here, what would typically be the noise, you start to realize that most of the protonated parent molecule peaks are actually there. We can check that by doing deuterated standard type of comparisons. So you can do isotope or deuterated standard comparisons in order to quantitate, and you can look at most of these particular species. In fact, we got here, I think, 11 out of the 14 species that we looked at were able to successfully identify just by looking at the NH plus peak. So with that, I think I'll just close, and I think I just want to come to the conclusion that simple plasmas such as the glow discharge have a lot to offer in terms of versatility. We can think of orienting them in different ways. We can think of exploiting their ion chemistry in both atomic and molecular spectroscopy. And I wanted to acknowledge my sources of funding as well as my co-authors, and to acknowledge you. Thank you for coming today, and to ask, actually, I'm not going to ask for any questions, am I? I'm just going to leave the stage. Thank you very much.